Hello. Yes. Can I contact you soon? I just want to lock it. Okay. Because we can't afford anything different. You know what? Yep. Yes, I will be coming back. Good. Good afternoon, everyone. Just give me a thumbs up if you can hear me and that you can see the screen. Okay, thank you. Okay, it's now 12 now. I'll start. Good afternoon, everyone. My name is Lucian Pullen. Uh, Today we'll be doing tutorial 3 on the laws of motion and tutorial 4 on work and energy. Okay, I did send you those questions that I'll be working on, so you can look at them like that. Now, pay no heed to the tutorial part. Okay, that is just for records for me and the team. What you need to be paying attention to is the actual problems which you have. Okay, so the first tutorial that we'll be doing, the first few set of questions will be on the laws of motion, and you have covered them so far. We should have done this last week, but due to the electricity problems that the area was experiencing, this studio that we stream out of has had no electricity, so we are one behind, but no worries. Let's look at question number one. Question one on the laws of motion says the following. The systems shown below are in equilibrium. It means there is no net force for all of those systems. If the spring scales are calibrated in newtons, what do these spring scales read? They tell us that to ignore the masses of the pulleys and the strings and assume the pulleys and the incline in figure 4 or figure D rather are frictionless. So first of all, we need to calculate what would be the readings on the springs, and then we need to ignore the masses of the pulleys and ropes themselves, and we need to assume that there is no friction in figure D. Okay, so let's go first to figure number A. Okay? Now I always try to do a force or free body diagrams to aid me in my solving of problems. Let me just make sure that everyone is reading. If at any point you have a question, please just stop me, raise your hand until, or keep it raised if I'm not busy there. I'm looking at multiple screens at the moment, so I might not see you for a few seconds. So keep your hand raised if you have a question. As for the particular problem, let's look at it. So all of these systems are in equilibrium. We need to determine the masses, or rather the readings on each of those springs, which would be forces. We need to determine the forces on each of those springs. And what do we need to do finally? We need to ignore the masses of the pulleys and strings. Now in the real world that won't happen, but here can ignore those masses. Now let's look at system A. Okay, what are all the forces on system A? Okay, if those forces are in equilibrium, that means that the sum of the forces must be equal to the mass times the acceleration. That is Newton's law. Okay. Now the sum of the forces in this case, let's pick just one of these samples, or not samples, this balls. Okay, let's just pick one. What is pulling this ball upwards, or this mass? It is the force of tension. Okay, so it's tension that is pulling it upwards, while what force is dragging it downwards? What force is dragging this ball downwards? It is gravity, Fg. Okay? It's the force of gravity. Okay? Now, these are the two forces. We just remember we want to find a reading on each one of uh, these spring scales. Okay, so we want to find a reading of these spring scales. Okay, in this case, we don't need to consider both balls. We only need to consider one. So the sum of the forces must eventually be zero because there is no net force. Okay, there is no net force. They are in equilibrium. Right? This is still the mass times the acceleration. But what are these different forces that are acting? It is the tension that is going upwards, and then the force going downwards is the force of gravity. Now another way of writing the force of gravity is just mass times the gravitational acceleration. Okay? There is a negative in front of that because I chose upwards as positive. Now this must be equal to zero. Tension minus the force of gravity must be equal to zero. Remember, that scale is just measuring the tension in the rope basically. So the tension is equal to mg. Okay? And if we work that out, that is 5 kilograms. That is a 5 kilogram weight multiplied by 9,81. And that gives us an answer of 49.0 newtons. That is the force. It's a 5 kilogram ball. That is the force of tension in this rope. In other words, that is also the force that is read on this spring scale. Okay, so we have answered question number one. If there are any questions, please ask now. Okay, those of you who are tuned in on YouTube, you can just type the question in the comment section. Okay, situation B, or what is happening in B? We have one ball. It is exactly the same problem as we just did. Okay, the answer to B would be exactly the same as the answer to A. The sum of the forces on that ball should be equal to the mass times acceleration. That is Newton's second law of motion. Newton's second law. Okay, and we know that the forces on that ball is tension, and then we have the gravity in the opposite direction. We've already seen that. And we know that the sum of these forces must be equal to zero because it is in equilibrium. Okay? So yet again, we are just working out the tension, and we've already done this. It's 5 kilograms multiplied by 9,81, which gives us, that's 9,81, let me rather write in the unit, 9,81 meters per second squared, giving us 49,0 newtons of force. on that spring scale for B. It's exactly the same as system A. Now, if I go too fast, you can just pause and then catch up. Okay? So, situation C. Okay, if you can see in your drawing there, let me see if you can see it. Yes, everything is still visible. We have two masters hanging from a pulley on both sides. There's a 5 kilogram masses. So this is the situation. We have a pulley. Not a, I can't seem to draw my circle perfect. There we go. That's as best I can do. We have one force this side and one force on that side. Let's call this force on this side T1 for tension 1 and the force on that side T2 for tension 2 to distinguish between these two forces, or rather, since these are both 5 kilograms, how about we just call it T1 as well, because they are going to be equal, okay, since they are both 5 kilogram masses. Okay, if they were not equal, we would have called them T1 and T2. Okay, and then before we forget, look where the scale is. Okay, the scale is here. It's up here. The scale is up here. So we want the tension in this part here. And let's call that T2. Okay, let's call that one T2. Now, we know from Newton's second law, the sum of the forces must be equal to mass times acceleration. But we know that the sum of the forces is equal to 0 because it's in equilibrium. Okay. Now, what are these forces? What are these different forces? Okay. If we take upwards as positive, it's T2 minus T1 on this side and T1 on that side. So T2 minus 2 times T1. And that is equal to 0. You rewrite it. Remember, we want the value of T2. Why? Because that is the tension. That is what's going to be on the spring scale, which is what we want. T2 is equal to 2 times T1, which makes sense. To the two students, I never noticed that it has stopped sharing. I just shared again. My apologies. Can you see it now? Okay, thank you. I think this software for some reason just kicked me out. But if you have YouTube open, that's fine as well. Let me just repeat this part. So in part C, we have this situation. Okay, we have the tension. We want the tension T2. Okay, and we have two pulleys on both sides. Each of them is 5 kilograms, so the tension would be the same for both of them. So we call them T1 and T1, and then we have a tension holding this whole system up on the pulley, which is T2, and it's T2 that we want. Now we know that the sum of the forces is equal to mass times acceleration. That's Newton's first law. And if we apply Newton's first law to this situation, we will know that, or we should immediately know that the sum of the forces should be 0. Why? Because the system is in equilibrium, there is no net force. Now, if we sum all these forces, we have T2 is going upwards. I chose upwards as positive, so I write a positive in front of it. The two T1s are pointing downwards, so I write negative in front of it, and instead of negative T1, negative T1, I write negative 2 times T1. It is the same thing. I'm just adding two negatives, which is negative 2. And if I take it over, I get T2 is equal to 2 times T1. So T2 is equal to 2 times T1. But what is T1? T1 is nothing but the gravitational force on this weight. So it's mass times gravitational acceleration. So it's 2 times 5 kilograms times 9,81. And that gives us 98,0 newtons. That is 98,0 newtons in this tension. Okay, so that's 98,0 newtons. Everyone happy so far? Okay, so the force on T2 is equal to 98,0 newtons. Now, this is the type of problems you're going to see in your exam and class tests. Okay, so moving on. Situation C. Okay, what is C looking like? It is an incline. This is arguably the more difficult of these problems. Problem 1, A and B was relatively easy. Also C, incline problems are usually the more difficult of these type of problems. Okay, so let's look at, if I was to draw a force diagram for this situation, this is how I would draw it. Okay, let me see. So there is a box. You can redraw this on your own time because I'm going to erase it, or rather, let me just draw it just one. Let me draw it here so I don't have to erase it. So this is the box. Okay, this is a force diagram. That's the box. Okay, there are multiple forces acting on this box. The first one is the tension. It's this one, T. And it's also that force that we want to calculate, because that is the exact force that will be on the spring scale. Okay, then I have the normal force acting always, since it's not sinking through the incline. And then what force is always there as well, pointing straight down? Me pointing straight down. It's the force of gravity, Fg. Okay, that's the force of gravity. Now, if there are any questions, you need to stop me and then speak, or you can text. Okay, so this is the situation for D. Okay, this is D. We have these forces acting on that box, and the box is 5 kilograms. It's a 5 kilogram box. Now, we know Newton's law, sum of the forces must be equal to the mass times acceleration. But we know, since all of this is in equilibrium, the sum of the forces is equal to 0. But what are these forces that are acting on this block? I'm going to draw, do this. This is going to be my axis. Okay, this is going to be my axis like that. So the sum of the forces are going to be, I'm only looking at the horizontal. So the sum of the forces in the horizontal component is equal to, there is the tension and then I subtract. What other force is in the horizontal? It is the horizontal component of the weight. Okay, so it's going to be the weight. So it's going to be the tension the horizontal component of the weight. So it will be the tension minus that horizontal component. How do you work it out? Or rather, not the horizontal component. Let me check something quickly. Yeah, the angle should be on this side. I just want to redraw that there, like this. So there's the angle. So this would be the horizontal component of the force here. This is the horizontal component of the weight. The horizontal component of the weight. You've all seen this in primary, or not in primary school, in high school physics, or in your study so far. How do you get this component of the force? Okay, it's the sine of that angle, and that angle is 30 degrees multiplied by the sine of 30 degrees, and that should give you your zero force in the horizontal component. Now for the vertical component, you only need that if you want to work out the normal force, but we are looking for the tension because it's the tension that's going to give us the reading on those scales. So the tension is equal to the horizontal component of this gravity. So it's mg times the sine of 30 degrees. Now mg, the mass is 5 kilograms. G is 9,81 meters per second squared. And then the sine of 30 is a half, if I'm not mistaken. It's one half. Sine of 30 degrees is one half. Someone just needs to confirm that. But if I remember my special triangles, it's one half. So it's 5 times 9,8 is 49. We've seen that before. 49, half of 49 is 48. That's 24, 24.5. So it's 24.5 newtons. That is the tension in that rope. That will also be the reading on that screen. Okay. Is there anyone with any questions regarding these four problems that we just did? Okay. You need to be able to do these problems backwards and forwards. If we give you the answer, you should be able to work backwards, say, with some guidance. But you need to be able to answer these problems immediately. Okay, especially the last one we just did, because that one comes out quite often. Okay, next set. Is there any questions? If you have a question, please just give me a thumbs up or raise your hand in the Teams meeting or in the chat for YouTube. Just give me a thumbs up or raise your hand and I will wait until you type out the question. Okay, any questions? Is there any questions? Any questions? If there are no questions, then I will continue. Any questions? It doesn't have to be about this particular work. It can be about your other work as well that you're currently doing in physics. If there are no questions, I'll continue. So here, what do we have here? Okay, three objects. Three objects. Three objects are connected on a table as shown in that figure. Okay. The coefficient of kinetic friction between the block of mass M2 and the table is 0.35. Okay, so we have the kinetic friction between block of mass M2 and the table is 0.35. These objects have masses of the following values or unit values or magnitudes. M1 is 4 kilograms, M2 is 1 kilogram, and M3 is 2 kilograms. It A asks us draw a free body force diagram of each object. Okay, so for each of those objects, draw a force or free body diagram. Okay. For option for mass M1, we have that is M1. Then we have a force going upwards, force going downwards. This is the weight of 1. This is the tension in 1. That is for mass 1. Okay. Then for mass number 2, this one is a little bit more involved. Mass 2 is slightly smaller. You don't have to draw it to scale, but I choose to. It has a normal force acting on it because it's on the table. Its weight, it should be exactly the same because there's no net movement up and down. So that's the weight of mass 2. That 2 looks like a 1. And then there are forces in the horizontal direction as well. In this case, the force in this case is T1, which is pulling it this way. T1. Remember, it's the same force T1 that is connected to block number 2. Block number 1, sorry. And then there is a force of tension T3 from block 3. And then there's also some friction. Okay. Now we need to determine quickly. Friction always opposes the net movement. In which direction is this block movement? Okay, in which direction is it moving? The heaviest block is M1, so I assume that M1 will be dragging it towards the left. That means friction would be towards the right. That's the force of friction, F, force of friction. So that is M2. If you did not understand anything, raise your hand. I continue because I assume that you understand what's going on. Now for M3, that's just the tension in M3. The tension in block M3 and we have the weight of M3, so W3. That's the force diagram for each one of these blocks or masses. Question B, what does B require of us? Question B says, determine the acceleration of each object, including its direction. So the acceleration of each object, including its direction. Okay. Now I'm going to erase this. Okay. Hope everyone understands how we got to that. We just drew all the forces that were on each of these blocks, that are acting on each of these blocks. Now for B, we need to draw, or rather we need to calculate the acceleration for each of those blocks. Let me look at my notes. For block 1, so for mass 1, the acceleration would be sum of the forces on block 1 is equal to the mass of block 1 times the acceleration of block 1. Now, what are the forces that are acting on block 1. What are all the different forces acting on block 1? We just determined it. It is the tension T1 going upwards, which I always choose upwards as positive, and then downwards we have the weight of block 1 pulling it down, and that is equal to the mass of m1 times the acceleration of m1. So we need a1 here, we need that acceleration. So we have that formula. We can actually write it further. We know the weight is nothing but the mass of m1 times the gravitational acceleration m1 times acceleration of 1. That is for m1. Now for block number 2, m2, for mass 2. What are the forces acting on mass 2? There are 4 of them. Okay. Now I'm not going to include the forces, the normal force and the weight, because they will cancel out. They are equal to each other. So I will just look at the tension, or let me rather write the sum of the forces on block number 2 should be equal to the mass of block number 2 times the acceleration of block number 2. Now what are all the forces that acting on block number 2? I'm discarding, or at this point I am not looking at the vertical components. Reason why is they will cancel eventually. So just looking at the horizontal components, if we remember, the horizontal components for this force would be T1 is pulling it towards the negative side. So let me write rather a minus there. I'm now thinking which one should I choose as positive. So, okay, let me write that as a negative. So towards the left is negative, towards the right is positive. Then we have towards the right is the force due to tension from block 3, and don't forget the frictional force, and that is will be the acceleration of block number 2 multiplied times its acceleration. Now, is there anything else we can put in for block number 2? Not really. We can write C3 force of friction as mu naught mu the mu k multiplied by the normal force. In this case, the normal force is just equal to its weight, which is mass times gravitational acceleration. That would be mass of 2 times m2. That will be m2 times a2, which is what we want. So we have one equation, we have a second equation. Let's look at block number 3. Block number 3, mass number 3, we have only 2 forces acting on it. That would be the sum of the forces on block 3 is equal to the mass of block 3 times the acceleration of block 3. Those forces acting on block 3 is the tension, which is going upwards, minus its weight, mg, and that is m3 times the acceleration of block number 3. Putting all of this together, we should have, this is equation number 3. We have now 3 equations, simultaneous equations, and we need to work them out. Okay, so these 3 simultaneous equations are as follows. It should be T1, if I remember correctly, minus mass of 1 times gravitational acceleration which is equal to mass of 1 times acceleration a1. And if I rewrite that, this is for mass 1. I have its mass is 4 kilograms multiplied by the acceleration of 1. But here's a weird thing that I did not write down, or I will write it at the end. The tension in 1 is T1 minus, that is 4 kilograms multiplied by 9,8. 9,81. So the first equation is actually T1 minus 4 times 9,8 should be 39. Let me just check. So why I have a calculator on here as well. 4 times 9,81 is 39. Yes, it is indeed 39.2. 39.2 newtons times 4 kilograms multiplied by A1. That's the tension in 1. That is equation number 1. Now for equation number 2, we had the tension negative T1, and then we had the force of friction positive, and we also have T2, T3 rather, positive, and then the force of friction, which is just point, it is the mu k, it is the, what was it again, 0.35, it is the coefficient of kinetic friction multiplied by the normal force, which is equal to, in this case, its weight, which in this case is m2, and that is 1 kilogram multiplied by 9,81, and that should all equal to 1 kilogram multiplied by A2. Oh, let me write it there, it can fit in there, A2. 1 kilogram, that is A2. So that's the second equation. If you have your force diagrams, this is becomes child's play. And then for the third one, we have upwards T3 minus the weight, that is 2 kilograms multiplied by 9,81. That's 2 kilograms multiplied by A3. Here is a weird thing. Okay, A1 should be equal to A2, which is equal to A3. Reason being, they are all connected by the same rope. So if one, and this is not a stretching rope, so if one moves, the others move. The rope is in tension, so if M1 moves, everyone moves. And since they're tied together, they all move at the same speed. Now here I have three equations, simultaneous equations. If you add these three equations up and take into account that A1 is equal to A2 is equal to A3, you should get the following. Let me just make this A1. They are all A1 now because they are exactly the same, so you can just equate them. Okay? So if you add all of this up, let's see. If you add up 4A1 plus 4A1 plus 1A1 plus 2A1, that is 7A1. Okay, so that's 7A1 on this side. Let me write that. I have no space here. On this side, it's 7A1. That is t plus negative t1 plus negative t1. Okay, you can do that all in your own time, but I will give you the final. What you should have on one side is, because I have no space, that is 7a1, or just write it as 7a. That's going to be the acceleration for everyone. And on this side, the t1s cancel, leaving us with 39.2 newtons. And you can go, I feel free to just check this, my math. If you add them all up, I'm not interested to know if you can add. If you add all of that up, it is then equal to, that's going to be longer, so I'll write 7a here. So it's going to be the T3s is going to cancel as well, because it's going to be negative on this side but positive going that side. So the tensions all cancel and you're left with 39.2 newtons. 39.2 newtons minus 3.43. Now your signs may be different to mine, okay? But then it will be consistently different. If I have a positive here, you should have a negative, and when I have a negative, you should have a positive. You'll still get the exact same answer. Minus 19.6 if you multiply it out. This is what you should get. If you add up all of those, this is the answer you should get. Now 39 minus 3.4 minus 19 gives you, if you add that quickly, let's look at what it is. They're all, you should be seeing this in your screen. That's 39.2. It's minus 3.43 minus 19.6. That's 16.7. 16.17. If you look there, that's 7 times the acceleration. Remember that 7 is a mass, 7 kilograms. That means the acceleration is 16.17 divided, oh, clear all, 16.17 divided by 7. That's 2.3. So the acceleration is 2.31 meters per second squared. That is what you should get. That is the acceleration of this entire system. So now we have the acceleration of the system. Okay? They asked us now in question C. Determine the tensions in the two chords. So you need to determine T1 and T2. Determine the tensions in the two chords. The tensions in the two chords. Let's take the first one. We have T1 going upwards minus the mass. It's 39.2 newtons. That is the mass. Remember, just always refer back to your force diagram. The acceleration we've already determined to be 2,3. This mass is 4. And then the acceleration is 2,31. So you have everything except T1. You can work out T1. Let me just make sure that I did the correct thing here. You should get, if you work it out, T1 should be 30 newtons. The tension should be 30. That's 4 times 2.31. Let's check. If and then you add 4 times 2.31, and then you add 39.2. So 39.2, clear all. 39.2 multiplied, or not multiplied, add to that 4 times 2.38. 4 times 2.31 times 2.31. That is 48.44. Just make sure. Oh yeah, this acceleration is going downwards, so that should be negative. Remember, we assume that the block, since M1 is heavier, it will go down, and since down is negative for me, that's going to be negative 4. That's 29. So T1 would be 29.96, which rounded up is just 30 newtons, which is correct. Okay, I was wondering why I had suddenly a different value. Don't forget your negatives. Remember, this block is sliding downwards. Okay, just remember that. If I forgot to include it in the second equation I wrote down, the acceleration is downwards. Okay, I may have forgotten that. No, no, it was right. I only need to include it here in this case. Okay, so D, we now have tension number 1, so we can now work out tension 2 as well. And if you continue finding one with like not tension 2, tension 3, in my case, I named it tension 3. If you want to find tension 3, it's equal to minus, it's 1 multiplied by 9,81, and that should be equal to 1 times 9,81. And there is I may have missed something here. This is for tension 3, it's going upwards, and its mass is going downwards. Oh, is the mass still? No, M2 is 1. M3 is 2, sorry. So there should just be a 2, 2, and there should be a 2. And the acceleration in this case, the block is moving upwards, so the acceleration is fine. So it's 2 times 9,81. 2 times 9,81 is 19.62. So it's going to be T3 minus 19.6. And this is going to be 19.6 newtons. It's also newtons. So T3 is equal to double that times 2. That's 39. I wonder whether I did something wrong here. I just want to check. Oh, sorry. Here's my mistake. I just realized my mistake. The acceleration here is 2,31, the one we calculated, remember, not 9,8. So this is 2, this is 2, this is also a 2. This will still be 19,6 newtons. Just forgot there that this acceleration is not 9,81. This is the acceleration of the whole system, or rather of block M3. 2 times 2.3, that's 4.62 newtons. And if we add those two, it should be, that's 6, it should be around 24.2 newtons. So T3, ladies and gentlemen, is around 24.6 newtons. Okay? Now, question number D. What is D? What does D require of us? If the tabletop was smooth, would the tensions increase, decrease, or remain the same? If the tabletop was smooth, would the tensions increase, decrease, or stay the same? If, first of all, if the tabletop was smooth, friction disappears, okay? And so the acceleration would become larger, okay? Friction will not be opposing the movement towards the left, so the acceleration would be larger. And for a larger acceleration, according to those equations, the larger the acceleration, for T1, it would, for T1, it would decrease, the tension would decrease for T1, and for T2, remember, just if you want to know why I say this, it's because T1 minus M1G equal to M1 times the acceleration. If this acceleration is bigger, that means this tension will decrease. Okay, it's moving downwards, so the acceleration here is negative. It is negative. Acceleration is negative because it's moving downwards, moving to that side. So it should be mg minus ma. If the acceleration is bigger, this decreases. This, however, increases because it's moving upwards. And it's all based on this equation there, T3 minus M1, actually M3 times G is equal to M3 times G. Okay, the acceleration is not G here, it's A increases if the friction is removed, A increases, and if A increases, T1 decreases and T2 increases. You can just, and the reasons are according to these formulas. Okay, quite simple. Question 3. Question number 3. A car traveling at 50 miles per hour on a horizontal highway. A car is traveling at 50 miles per hour on a horizontal highway. What if the coefficient of static friction between the road and the tires on a rainy day is 0.1? What is the minimum distance in which the car will stop? Okay, what is the minimum distance in which the car will stop? Now we need to use Newton's second law. Okay? And then B, what is the stopping distance when the surface is dry and the coefficient of static friction is 0.60? First, we need to determine the maximum. Well, the formulas. First of all, let's look at the formulas. Okay, V final. So we need a formula that includes initial acceleration, initial velocity, final velocity, the distance, and what do they want? That's all. So we need a formula that has acceleration, distance, and initial and final velocity. And I can think of only one that has all of those, plus 2 times the acceleration times the change in the distance. Right? We use that formula. Now what do we want? We want the minimum distance. If we rewrite this, we have the final velocity equal to the initial velocity squared. The final velocity, initial velocity squared, plus 2 times the acceleration times the final distance, x final minus x initial. We want that final distance. How long does it take to come to a complete stop? Now, x initial in this case will be 0. Okay, x initial is 0. Why? Because that's what we start measuring the distance. Okay, so x initial is 0. V initial is 50 miles per hour. We have that 50 miles per hour is 22.4 meters per second. You can check this. 22.4 meters per second. 22.4 meters per second. You can just convert from miles to meters per second. That's easy enough. Initial, sorry, should be initial. And it's all in V final. The final velocity should be 0. Now, this is the formula. If we plug in all of these answers and rearrange them to get the final distance, we have V initial squared over 2 times what? The static coefficient of friction times the gravitational acceleration. Now I'm going to explain now why that is the case. I just want to make sure about something here. My pen is thinner. Here, V initial. Okay. We also know that V initial squared is equal to, remember this is now 0. Maybe I should make a space there somewhere. The formula. Let me rewrite this formula. Okay, if we plug in everything that we know so far, V final is 0, V initial is still there, squared, plus 2 times the acceleration times xf is, Vf is negative, so that leaves us with xf. Let me just see there. Okay, just someone. I'm just checking if someone's asking anything. So xf, nothing. That's 2a. Xf is what we want. We want the distance x. That's 0. So we have xf is 0, x initial is 0, v final is 0, and then v initial is 22. Okay, so if I rewrite this is vi plus 2axf. Okay, 2axf. That's 0, that falls away. That's square. This is 0. Okay. Oh. Going to a next page, please remember this formula 2axf. If we go to the next page, we know that acceleration in this case is equal to the static coefficient of friction minus minus the static coefficient of friction times g. Okay, that is the acceleration. Okay, you can prove that. Okay, now remember we had a formula now. It said v, it said 0 is equal to v initial squared plus, this is what the formula said, 2axf. This is the formula that we found, but we now also know that acceleration is negative us g times xf. And we want what? Xf. We want the formula for xf. And if we write xf down, we take vi over, it becomes negative vi, and we divide by a negative, so it's negative divided by a negative, 2 mu s g. Okay? Negatives become positives, and this is what we get, 2 mu s g. And if we plug in all our values, we have initial is 22.4 squared over 2 times, what was the static friction? 0.1 multiplied by 9,81. We have that the stopping distance is 256 meters on a rainy day. Now on, what would happen on a dry day? Okay, on a dry day. Now normally you can just reason some of these stuff out. You know that on a wet day it takes a car longer to come to a stop. So we should expect a number smaller than 256. Okay, so B, the formula still stays the same, xf. The only thing that changes, I've already shown you how I got to this formula, is the fact that this changes. The static coefficient of friction is the one that changes because it's now a dry day. This is still 22.4 squared 2 times, this is now 0.6 times 9,8, and the answer is now 42.7 meters. Check this difference. On a rainy day, it takes it 256 meters to stop. Okay, so 256 meters to come to a stop. But on a dry day, it just takes 42 meters to stop. 43 meters basically. So yes, this is a very good problem. Let's look at problem number 4. A woman dragging a case. A woman dragging a case. Question 4. Let me show it there. A woman at an airport is towing her 20-kilogram suitcase at a constant speed by pulling on a strap at an angle theta above the horizontal. She pulls on the strap with a 35 Newton force. Okay? And the friction force on the suitcase is 20 newtons. Draw a free body diagram of the suitcase. Okay, so A, we need to draw a free body diagram of the suitcase. So that's the suitcase. This is the applied force from the woman. We have the force of friction going this way. And then we have the weight, the force of gravity going downwards. This will be the normal force going upwards. So now we have all the forces on the suitcase. That's theta, the angle. Okay, so we have drawn a free body diagram. B, they ask us what angle does the strap make with the horizontal? What angle does the strap make with the horizontal? What angle does the strap make with the horizontal? Now you know that the mass of the suitcase is 20 kilograms. You know that the force it's being pulled is 35 newtons. You know that the sum of the forces in the x direction should be equal to the mass times the acceleration in the x direction, and that is equal to the forces in the x direction is the friction force, which is negative 20 newtons, plus the horizontal component of the force being applied, which is F, the force being applied, times the cosine of theta. And that should all be equal to 0, because it's not accelerating. Then the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction, negative, or rather, let me know it. It is the normal force minus the weight it's minus Fg minus another force, that is the horizontal component, or rather, yes, the horizontal component of this force that it's pulling with, the vertical component, sorry, and it is positive F sine of theta. So you have one equation here, two equations. Okay, so now you have two equations. Okay, and if you work out F cosine of theta, that's equal to 20 newtons. If you rearrange that, F cosine of theta, that's also equal to 0. It's equal to 20 newtons. So cosine of theta is equal to 20 newtons divided by the force. And we've already been told that that force is 35 newtons. So the cosine of theta is just that. So theta, therefore theta is equal to 55.2 degrees. That is what theta is. Okay? If you don't understand, please help me so I can re-explain. Someone asked, will the tutorials be saved? Yes. Yes, they will be saved. Okay, so theta is now 55.2 degrees. C. you need to calculate what's the magnitude of the normal force. Okay, so N, the normal force is just equal to the force of gravity minus the applied force F sine theta. So the force of gravity is nothing but 196 newtons. That is just the mass of the case. In this case, 20 kilograms multiplied by 9,8. Before people start wondering where I got this, it's 20 kilograms multiplied by 19,8. Oh, sorry, not 19, 9,8. 1 minus this force is 35 newtons, sine of 55 degrees. Sine of 55.2. Sorry, I just used 55. So that should give you an answer or a normal force of 167 newtons. 167 newtons. And that is all for question number 4. Our last question for laws of motion is question 5. A 40-kilogram child swings in a swing supported by two metal chains. By two metal chains. Each is 3 meters long. The tension in each chain at the lowest point is 350 newtons. Find A, the child's speed at the lowest point, and B, the force exerted by the seat on the child at the lowest point. And importantly, ignore the mass of the child. Okay, now this is the seat. Let's say this is the seat of the swing. There are two forces on this. What is the first question? They need to find A, the child's speed, and B, the force exerted. So the force vectogram is like this. There will be tension in each of these chains because the chains are each exactly a certain length. They are at the exact same length. And of course, we assume that the child is sitting exactly in the middle between these two chains. And then, of course, the weight of the child, the mass of the child is the other force. That is the force. And of course, if we take a look at the force on the seat itself, is the weight, and then the normal force pushing the seat upwards. So, the sum of the forces on the seat is equal to the net force is equal to 2 times the tension going upwards minus the weight of the child. And that should be equal to the mass times acceleration. But in this case, since it is in an arc, okay, it is in an arc. Why? How do we know that this is in an arc? Because it's a swing, so it's part of a circle. So circular motion, and that would be acceleration due to circular motion is v squared over r. So we can write it like that. So F net, the net force, is equal to 2 times, what's the tension? 2 times the tension is given as 350 newtons. It is given in the problem, 250 newtons. 350, excuse me, minus the child has a weight of 40 kilograms and 9,81. That is the net force, and it's equal to mv squared over r. Okay? If we do all of that math, the answer comes out to 308. 308 newtons equal to the mass mv squared r. Okay? Now, what is the radius of the circle? Okay, it would be the length of that. The radius of the circle r would be equal to, I'm going to continue here. Oh, let me rather not do that. I'm going to continue here. Up there, up there. I don't want to remove anything. So it's 308 is equal to 308 newtons equal to the radius of the circle. Remember, we're just concentrating on the arc for this moment, but it completes a circle, is the length of those chains. And the length of those chains is 3 meters. The velocity is squared, which is what we want. We want the velocity, and the mass of the child is 40 kilos. So if we solve for v squared, or rather just for v, we get that it is 4,81 meters per second. So 4,81 meters per second is how fast the child is going at the lowest point. Now B, they want the normal force. Let me just check what they want. B, the force exerted by the seat on the child at the lowest point. The normal force from the seat on the child accelerates the child in the same way that the total tension in the chain accelerates the child. Therefore, the normal force in this case is going to be 2 times the tension, because of what I just said, the normal force from that seat. Okay, the normal force putting this must be equal to the tension in the chain. So it will be 2 times 350 newtons. So that is 700 newtons. Okay, and then we're done with our section on motion, okay, and Newton's laws of motion. We can now go to the questions on work and energy, which should be much easier, I think, or you should be just have finished that section recently. Work and energy. Let me just change this here. Okay, yeah, there's the problems on work and energy. Just make sure it's in. Okay, the problems tutorial number 4 on work and energy. Let's look at work and energy. We're done with Newton's laws. Tutorial 4. This is work and energy. Wonderful. I want to see if it's actually showing the new. Okay, work and energy is there. And if you can't see, don't worry, I did email all the problems to everyone. A shopper in a supermarket pushes a cart with a force of 35 newtons directed at an angle of 25 newtons below the horizontal. The force is just sufficient to balance various friction forces so the cart moves at a constant speed. Find the work done by the shopper on the cart as she moves down a 50-meter long aisle. B. The shopper goes down the next aisle pushing horizontally and maintaining the same speed as before. If the friction force doesn't change, would the shopper's applied force be larger, smaller, or the same? And then C. What about the work done on the cart by the shopper? Okay, first, question 1A. The first part. A 35 Newton force applied by the shopper makes a 25-degree angle with the displacement of the cart or the horizontal. The work done on by the shopper is then, we know that work is equal to force times distance. So the work done by the shopper, so I'll just say WS, work done by the shopper is equal to the horizontal force. In this case, it's force times the cosine of theta times the distance x. In this case, the force is how much force is being applied? 35 newtons, 5.0 newtons times the cosine of theta, which is 25 degrees. And then finally, the distance is 50 meters. And that gives us an answer, or the work done is 1.59 times 10 to the 3, or 1.59 kilojoules. That's the work done by the shopper. B. The shopper goes down the next aisle pushing horizontally and maintaining the same speed as before. If the friction doesn't change, would the shopper's applied force be larger, smaller, or the same? They want to know, okay, if the friction force doesn't change, would the shopper's applied force be larger, smaller, or the same? Would the applied force be larger, smaller, or the same? So we're just looking at the applied. So if the friction doesn't change, so the friction stays the same. That, okay, so the friction force doesn't change, but that is a problem. The reason why I'm saying that, oh, would the shopper's applied force be larger, smaller, or the same? It will be smaller. I'm thinking about the friction now. We should be thinking about the shopper's force. It would be smaller. The reason is when you're pushing at an angle, okay, there is a vertical component of this force, okay, a vertical component. Now suddenly the shopper is pushing horizontally, meaning there is no more vertical component. Now what this vertical component did, okay, this vertical component increased the normal force on the car. It increased the normal force on the car. And if the normal force was increased, the force of friction was increased. And if the force of friction is increased, and if there is no more increase in the normal force, the force of friction is lower. Right? And but we remember we are still moving at a constant speed, which means since the force of friction is lower, the applied force to get that same speed is now lower because the force of friction is lower. And that is why the applied force should be smaller. Now, since the horizontal component of the force, just check it out for yourself, okay? This force is at an angle, okay, upwards, at an upwards angle, which means it helps the normal force. Okay, makes the normal force larger. And the larger the normal force, the bigger the friction. But since we remove that addition to the normal force, the frictional force is smaller. And if the frictional force is smaller but the speed stays the same, the applied force must be smaller. So the Chopper's force is smaller. C, excuse me. Since the horizontal component of the force is less in part B, the work, what's the question? What about the work done on the card by the shopper? The applied force is now less. They tell us that they apply. What about the work done on the card by the shopper? Okay. So since the horizontal component of the force is less in part B, so that horizontal component is now less, the work performed by the shopper over that same 50-meter distance is the same as in part B. Okay. Let's reason this out. The horizontal component of the force is less. We've already established that the horizontal component of the force is smaller. It's still the same distance. So, if the horizontal component of the force is less, the work done is less. Sorry, the work done is less because the horizontal component we calculate work based on F times W. There is no more horizontal component, so the work is less. Actually, the force is more. Cosine theta, so the horizontal component of the force is now increased. So if the horizontal component of the force of this is increased, then the work done is increased because there is now it's now horizontal, which means that the entire force, not just a fraction of the force, the entire of the force, which means the force is increased. It's no longer a fraction of the force, it is the full force of 35 newtons. It's no longer a fraction of 35 newtons. It's the full 35 newtons, which means the work done now is more. But we've already established that the force is smaller. So let me just go back to here, this one, smaller. The vertical component, the force, is completely horizontal. So it will equal the friction force since the cart stays at a constant speed. Okay. The horizontal component of the force and the friction should now be completely equal. Okay. Now in part A, the Chopper's force had a downward vertical component, increasing the normal force on the car. But in this case, there was no vertical component, so the normal force the friction force will be less, which means the force is smaller. And if the force is smaller, the work done is less. That is what you would tend to think, but I am now just thinking, since the frictional force is also smaller and the work is also smaller, the frictional force is now smaller, it will be the same. Reason being, why this is the same is the fact that even if though the applied force is smaller, the friction is also smaller, which means the total net force is still the same. I was having a bit of a moment there. So I finally figured it out. Well, I had it here as the same, but I was wondering why it is the same because I used an example to calculate. I was just looking at my example. The applied force is smaller, yes, but the friction is also smaller, which means the work done is still the same. And that is the correct answer. 2. A block of mass m. I just put it up. A block of mass m equal to 2.5. A block of mass m equal to 2.5 is pushed a distance d equal to 2.2 meters along a frictionless horizontal table by a constant applied force of magnitude F equal to 16.0 newtons, directed at an angle of 0.25, 0.25. So it's like that, like it's in the drawing. There is a force of magnitude 16 newtons directed at an angle of 25 degrees below the horizontal as shown in the figure. That is above the horizontal. Determine the work done on the block by the applied force, by the normal force exerted by the table, the gravitational force, and the net force on the block. Okay, so we need to determine the work done by all the different forces on the block. The applied force does the following work. Work is equal to F times X, the distance. In this case, the force is F times the cosine of 25 degrees multiplied by the distance X, which in this case, the force is 16 newtons. Cosine 25, cosine of 25 degrees multiplied by the distance 2.2 meters. The work done is 31.9 joules. The work done on the block by the applied force. Now, the work done by the normal force. And then the work done by the force of friction. Okay? Normal force and the force of friction are perpendicular to our direction of travel. So B and C are perpendicular. So the force, they are at 90 degrees. So they do zero work. Okay? Zero work is being done. D, the sum of all the work is equal to 39.19 joules plus 0 joules plus 0 joules. That is 39 or 31.9 joules. That is the total work done. So you can add work like scalars because it is a scalar addition. Number 3. A force F, 6 units in the I direction, in the I head direction, and 2 units in the J head direction, acts on a particle that undergoes a displacement delta R. Find the work done by the force on the particle and the angle between F and delta R. Okay, that's easy. So the work is always going to be force dot delta R. So it is Fx, the horizontal component, times x plus the horizontal vertical component times y. So 6, this is 6 times 3 plus -2 times 1, and the unit is Newton meters or joules. 6 times 3 is 18 minus 2, that's 16.0 joules. Okay. It's component wise. When you multiply two component wise vectors, you multiply each individual direction. That's A. What does B require that we do? The angle between those two. The theta between those two is equal to, I'm not going to go into the math of why this is, but it's equal to the cosine, the inverse cosine of the dot product of those two vectors. You should have done this over the magnitude F delta R, over the magnitude of these two vectors F delta R. Sorry. The magnitude of these vectors multiplied. So it should be cosine negative inverse. There is 16. We just got the 16 Newton meters. And then the magnitude of that vector multiplied by the magnitude of that vector. I should have written that like that. So the magnitude of that vector is just 6 squared plus -2 squared multiplied by the magnitude of that vector is 3 squared times 1 squared. Oh, let me rather write this part on a new page. Cosine inverse, that is 16 newtons per meter. This one is 6 squared plus -2 squared times the square root of 3 squared plus 1 squared. That should give you theta, and that is equal to 36.9 degrees. That is theta. This is baby math. The next problem is about a bullet, and then one after that is about a crate. So, question number 4. A 100-gram bullet is fired from a rifle having a barrel 0.6 meters long. Okay. Choose the origin at the location where the bullet begins to move. Choose the origin to be at the location where the bullet begins to move. Then the force in newtons exerted by the expanding gas on the bullet is a function in terms of distance. A. Determine the work done by the gas on the bullet as the bullet travels the length of the barrel. That's easy. So the work is equal to the integral from the starting point to the finish point of F dot R, dr. So the integral. It starts at 0 and it ends at point 0.6, the length of the barrel. The function for the force is 15,000 plus 10,000 x minus 25,000 x squared. That is the function dx. So there you integrate all of that. If you integrate it, you get 15,000 x minus 10,000. If you remember your rules of integration, x squared minus over 3, that's 25,000 x cubed, 25,000 x cubed, x cubed. Okay, from 0 to zero point 0.6, if you do the integration correctly, it will be 9 kilojoules plus 1,8 kilojoules minus 1,8 kilojoules, leaving you with an answer of 9 kilojoules of work is being done by this gas on the bullet. Next question, B. B. If the barrel is now a meter long, how much work is done? So the only thing that changes is the distance. It is now a meter long, so you do the same thing. You plug in where x is. This is the formula that we came up with, or we integrated. It is 15,000 times x, and where x is, you plug in 1 meter. That is now pass. It's 2. That's 10,000 now. Remember, that's 1 squared. And then the last one is negative. That's 25,000. That is 1 cubed over 3. If the barrel has become longer, the work need done, the work that needs to be done is more. It is now 11 kilojoules. That makes sense because work is force times distance. If the force stays the same, but the distance changes or gets longer, the work gets more. And C, what is C? How does this value compare with the work calculated in part A? The work is greater. Okay, work is greater, and you can work it out the percentage. Okay, work is greater. This is what we just said. The work done is greater. And you can actually work it out as a percentage. Subtract this from the previous one and divide it by, take 11, subtract 9, divided by 9, and you should get a percentage. And that will tell you how much greater. Anyways, last question for today. A crate of mass 10 kg is pulled up a rough incline with an initial speed of 150 meters per second. The pulling force is 100 newtons parallel to the incline, which makes an angle of 20.08 with the horizontal. Okay. The coefficient of kinetic friction is 0.4 and the crate is pulled 5 meters. How much work is done by the gravitational force on the crate? So the work done by the gravitational force, let's first draw the situation. This is a rough incline. It makes an angle of 20.08. This is the crate. It's being pulled upwards by a force of 100 newtons. There is a force of kinetic friction, Fk. Then gravity goes down, Fg. This is the forces on this crate. So the work done by gravity is the first one. It is force times distance. In this case, the force of gravity is mg times the cosine of 90 degrees plus theta times L, the distance. Mg, the mass is, what's the mass of this crate? It's 10 kgs times 9.8, 1 times the cosine of 90 plus 20.2, that is 110.02. So let's just say 110 degrees times the length is 5 meters. No, 5 meters. The work done by gravity, therefore, is negative, and it's 168 joules. Gravity does negative work. Okay. B. B. So we set the x and y axis parallel to the perpendicular to the incline. We know that. First of all, the question: determine the increase in the internal energy of the crate incline system owing to friction. Okay. So the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. So the forces in the y direction is the normal force minus that cosine. I just want to make sure. Yes, the cosine. It's the cosine. It is the gravitational force times the cosine of the angle. The reason why it's not sine, just check your angles there. So it is the normal force minus 98 times the cosine of 20 degrees. I'm just not going to 20.02, just going to use 20. And that should be equal to 0 because it's not moving up and down. So the normal force is equal to 92.1 newtons. So that is the normal force. So now we have the normal force. They want the force of the increase in internal energy due to friction. So now we have the normal force. What is friction then? The force of friction is equal to the coefficient of friction times the normal force. In this case, the coefficient of friction is 0.4 times the normal force, 92.1 newtons. So 36.8 newtons is the force of friction. So we have the force of friction. Okay, the change in the internal energy. Therefore, the change in internal energy, this is a formula you should know, is equal to the force of friction, Fk, times distance. It is 36.8 newtons multiplied by the distance of 5 meters, and that is equal to 184 joules. That is the change in the internal energy. C. What is the change in the kinetic energy? Oh, sorry, we need to see how much work is done by the 100 Newton force. So work is force. Okay, my angle is um, work is equal to force times distance. It's 100 newtons. Distance 5 meters. The force is 500 joules. D. What is the change in the kinetic energy? Okay, so the change in the kinetic energy is equal to the negative of the force of friction, or the negative of the change in the internal energy, plus the sum of the work done by other forces. So we're just adding all the forces. And those other forces, is the force of friction times distance, of course, times distance. That's the work done by gravity plus the work done by the applied force, which you just work. We work this out first. We have worked this out, and we have worked out the work done by the normal force. If you add that, all of it, it's negative 184. We work this out. Minus 168. Work this out. Very first is the work done by gravity. Just making sure we have the applied force as 500 joules of energy, and then 0 joules for the work done by the normal force because it is perpendicular, it's at 90 degrees. Therefore, the answer is 148 joules. The change in the kinetic energy is 148 joules. Okay. And then the last question. What's the speed of the crate after being pulled 5 meters? What is the speed of the crate after being pulled 5 meters? Now we know delta K is equal to K final minus K initial. Just checking something. That is a half mass final velocity squared minus a half mass initial velocity squared. And if you plug in everything, it is, we just worked out that this is 148 joules. This is a half times the mass is 10 kilograms. The final velocity is we want the final velocity Vf squared minus a half times 10. What's the initial velocity? 1.5 meters, 1.5 meters per second, and that is squared. And if you solve for Vf, you will find that Vf is equal to 5,65 meters per second. And that, ladies and gentlemen, is all the time that we have for today. I hope you enjoy these problems, and when you eventually do them, that you actually understand what is happening and can follow the math. Thank you, and I will see you next week.